This is an example of the kind of thing you want to be able to do with all of this NMR information. If you're given a spectrum and a clue about what compound you're dealing with, the idea is to come up with its complete structural formula, show how all the atoms are connected. So in this case, we're told we have something that's C4H8O, and we're supposed to use this graph here to figure out exactly what that compound is. And you can see the answer is given on the next slide. So if you want to, you can pause this right now and take a look at this and see what you can piece together. If you want some more clues, well, we can start to write down what fragments must be present in order for the molecule to produce these peaks you see. First thing I notice is that this thing has a single hydrogen resonating way above 9.0. That's consistent with this being an aldehyde. So for one of those 4 carbons, we could just draw what would be an aldehyde group, and that particular hydrogen should give a singlet with that kind of resonance. Notice this singlet has a little bit of splitting going on, but labeling it as singlet means we shouldn't expect that that's going to correspond to any type of splitting that we can make sense of. So anyway, that takes care of one of my 4 carbons, takes care of my oxygen and one of those 8 hydrogens. Well, what's left is a group of peaks. Well, this one's worth 6 hydrogens, and then this one is just worth 1, so that's my other 7 hydrogens, and so 6 of them are equivalent, and then there's 1 that's separate from those. And this doublet septet pattern is something we've seen before that tells me how the rest of those carbons should be put together. Anyway, think about the rest of this and what you can do to draw a structure that will match this. Another approach that's sometimes useful, especially when we only have a few carbons in our formula. Now that we know that it's an aldehyde, well, there's not a whole lot of aldehydes with 4 carbons that's capable of existing. So you could just try to draw a 4-carbon aldehyde and see if your guess matches this spectrum, and that might suggest if you need to make some tweaks to your formula to make it match up. Sometimes it's helpful if you've got one structure there to kind of use as a guideline. Anyway, we'll flip over here and see what the answer looks like. And this came out of your textbook, which is why it looks like some of the other examples I've shown you. This is the structure, 2-methylpropanal, because when we have 6 equivalent hydrogens, and especially when they are coupled to a single hydrogen on an adjacent carbon, that suggests that isopropyl group. 6 carbons will be equivalent, 6 hydrogens will be equivalent if they are attached to 2 methyl groups on the same carbon. And they should be split into a doublet if that carbon has another hydrogen attached to it, and at the same time that hydrogen by itself is going to give rise to a septet because it's being split by those 6 yellow shaded hydrogens. So that's the kind of thing we can do if we have a formula with not too many atoms in it, and if we're able to see how the hydrogens are split, in this case into a group of 6, 1 and 1, that gives us a big clue as to how this thing might be put together. So that's the kind of thing that, again, on the worksheet you'll be getting more practice with. Here's another example. It's already worked out. We've got our structure and our NMR spectrum here. Both of those compounds, their names certainly aren't the same, but their structures look a lot alike. And in fact, you have to look close to kind of see what the difference is here. And it has to do with where this oxygen is. Notice there's an oxygen here that's to the left of that carbonyl, and that same oxygen over here is to the right. Both of these are esters. Both of them are, well, they're isomers of each other, so their spectra should look a lot alike. But the place where their spectra are different has to do with the environment around that, that oxygen there in the middle of that chain. Back up, and you can see if you look down at the way these are coded here, what's labeled as the C hydrogens here. Notice that C there is telling me that this peak goes with those 2 hydrogens there, and That is a triplet because it should be split as such. Well, those same two hydrogens on the spectrum below, notice they're way over here, because in this second molecule, that CH2 group is not directly connected to an oxygen the way it is up above. And so that makes the resonance for those hydrogens labeled as C here, it makes the resonance quite different. A little above 4 when they're next to that oxygen, down here around 2.5 when they're not. And at the same time, the ones labeled B here, notice how that peak changes. Here's the hydrogens labeled as B in this top spectrum, and look at the corresponding hydrogens down below. We've gone from, again, a little over 2 parts per million to up here a little above 4. Because when we move that oxygen to the right side of that carbonyl, now that oxygen is very close to those hydrogens labeled as B here. Everything else about the two spectra match up pretty nicely, but it just kind of shows us that even when you have a very subtle difference in structure, the NMR can oftentimes can show differences that allow us to, in this case, tell the difference between these two esters that are isomers of one another.